Good morning, everyone, and welcome to our second day of the iFishIENCi Research and Innovation Action Project Final Meeting. Yesterday, we talked about the project as a whole, and specifically the product iBoss. And today, we're going to talk about the topic of sustainable aquaculture through the lens of circularity. So, I'm going to hand it now over to my colleague Montse from Leitat in Barcelona. And a reminder for those online that any questions or comments you have, please put those into the chat and we will bring those into the discussion. So, Montse.
Thank you, Dorothy. Hello, good morning, everyone. My name is Montse Jorba. I work at Leitat Technological Center, Spain, and I'm area manager in the Circular Economy department. So, on behalf of the iFishIENCi partners, welcome to this technical workshop. We would like to thank the attendants, to all you people here, audience that we have here in the room, and the audience that we have online. So, as Dorothy said, yesterday we were focused on the aquaculture 4.0, and we were also discussing about the iBoss product, and it was amazing. But today is time for the circularity in aquaculture. As probably you know, the aquaculture activity has an important role in the transition to the sustainable food chain, and not only in the sustainable food chain, also in the circularity in general, in the bioeconomy. So we have important challenges that we have been working during the iFishIENCi. So today we will talk about waste. We will talk about waste management. We'll talk about collection of the waste, and we will talk about circularity in the context of the circularity. So specifically today we will have time to discuss about regulatory framework in aquaculture. We also we will present results in the waste management in the RAS systems. We will present also results in the valorization context and the circularity assessment. And finally, we will explain, we will show the Waste2Value product. So, well, today we have a very tight agenda. We have 6 presentations and 6 speakers, all them from the iFishIENCi partners, the iFishIENCi project. Well, we will have 10 minutes presentation, and at the end of each presentation, we will have about 2 minutes for questions and answers. So, well, we are really proud to show our main results, our achievements, but we really would like to receive your feedback as audience. We would like to have your perception about this topic. Well, after the presentations, we will share our email addresses. So if it's not possible to answer your questions, we will have time to answer it by email. So let's start with the first presentation. Muhammad Eusha from TTZ Bremerhaven from Germany, please, the floor is yours.
Oh, thank you, Montse. Is everyone able to hear me? Hello? Yeah, thank you. So, thank you and good morning to everyone. My name is Yusha. I represent TTZ Bremerhaven. So our role here in the framework of, well, within the scope of iFishIENCi was to discuss to investigate the regulatory framework, which we have done. In fact, it was principally done by my esteemed colleague, Mary, but she's going to be on maternity leave and thus is unable to travel today. Nevertheless, I will try to basically summarize what she has done over the course in the course of the project. Yeah, so I think it's from here. Okay, so there happen to be quite a few regulations and legislations within the European, in the European Union with regard to aquaculture, and this these focus on different aspects of aquaculture, and at the same time different types of aquaculture practices. So, for example, you have circularity and waste and water management. These are the aspects of aquaculture which are in detail dealt with by the regulatory framework available. And at the same time, the different types of aquaculture practices that we have, open cage aquaculture, RAS aquaculture, these are also within the framework of the regulatory framework. And all these are essentially inspired by some of the principles that the EU believes in, obviously. For example, the principle of circularity, no waste, zero emission. We all are familiar with these keywords. So what the EU essentially does is it issues directives, which are essentially suggestions, recommendations, and then based on these recommendations and suggestions, the states, the individual member states, they enact their individual legislations. So what is the waste? The Waste Framework Directive, which is one of the many directives the European Union has issued, it basically defines waste. I mean, we all know what waste is, of course, but the formal definition is any substance or object which the holder discards or intends or is required to discard. And then we have another document of relevance, the European List of Waste, which stipulates that you have two kinds of waste which are actually relevant to aquaculture. The first is waste from agriculture, horticulture, forestry, hunting. So that is one type of waste. And the other is waste from preparation and processing. So these are the two kinds of waste that we have within the scope of the legislation. And the legislation is based on a few main pillars. Principally, the principal one is Urban Wastewater Treatment Directive and nitrates. So there are four of them. The first is Urban Wastewater Treatment Directive, and you also have nitrates pollution from Agriculture Sources Directive, and then you have Water Framework Directive. That is the flagship of the EU water policy. And then you have the Environmental Quality Standards Directive. So these four together, they constitute the bulk of the regulations that you see. They direct bulk of the regulations in the EU states. But you have some minor directives as well, which are quite relevant. The Industrial Emissions Directive, for example. The REACH legislation, that is another one. Biocidal products regulation, Veterinary Medicines Directive, Plant Protection Products Regulation, and regulation on persistent organic pollutants, on which we did some more extensive study, we would say. Yeah, so just to give you an example, the recirculating aquaculture system, if you would like to find out the EU's recommendations and policies on it, you have to go to Water Framework Directive. If you want to study the EU policies on open cage aquaculture, you have to go to the Marine Strategy Framework Directive. So these are somewhat separate in a way. And at the same time, of relevance to both these aquaculture systems, you have these relevant directives as well. The Code of Conduct of Responsible Fisheries, Convention of Biological Diversity or the CBD, that's also there. And there's some multilateral agreements which are also of importance in terms of local state level regulations. So we also have the question of POPs, which is, I think, a concern that the consortium had when we were considering the waste-to-value concept, when we were evaluating it for its practicality. So these are basically non-polar, lipophilic, and ubiquitous environmental contaminants, and they're called persistent organic pollutants because they tend to have an unusually long, they do not degrade with time, which is obviously a huge issue. So the two relevant regulations with regard to POPs are the Directive 2002, as you can see, I've listed them there. So this one, the first one, actually, it discusses, it's dedicated to POPs, and the second one only peripherally mentions POPs. And while there happen to be a number of regulations, one has to recognize that it's very difficult to, sometimes reconcile the perspective of aquaculture and POP. So one might find it difficult to find relevant information with regard to what we have in mind. So that's, for example, you have here the level of POPs, the permissible level of POPs here, 0.75 milligram per kilogram for dioxins, but this is specifically for the feed. But then again, if you consider sludge, if you wish to reuse sludge, reintroduce sludge, that is, and use it as a feed after processing, that is, there happen to be some regulations which forbid this. So this is I think, a very good example of how legislations are often, they're very difficult to interpret and make sense of. So that is perhaps one area that we could assist the European Union with our expert, your expert recommendations. But so similarly, you can see here for particular very specific chemical compounds, they have listed some boundaries here in these regulations. So I think it would also be relevant to discuss some regulatory barriers. I think that would be of interest to us. Do I have more time?
Yes, more.
Okay. So one problem is with, I have listed them very briefly here at the bottom. The principal barriers that we have in terms of regulations. You have multi-level governance barriers where you have palpable conflicts between either different legislations because you have cross-platform legislation sometimes which are very important and relevant from the perspective of waste-to-value, I think, because it is often the case that you have it's very difficult to isolate aquaculture as a body. It is, of course, a part of nature, and sometimes one regulation has a conflict with another regulation. So that's a problem. And then you have national and local regulation issues where you pretty much face the same problems, but at a national state level. And then you have licensing issues, which happen to be quite a problematic issue, actually. In Norway, for example, I think the licensing is quite convenient compared to how strict it is in Germany, for example. The regulations are very strict and sometimes unnecessarily so, one might say. It makes it difficult for anyone to obtain a license. And then you have barriers regarding the use of wastewater from aquaculture. So the EU regulations are quite comprehensive when it comes to wastewater treatment, what we can do and what we can't do. But it's not seen from an aquaculture perspective, so that has to be taken into account. And I think there is quite a bit of room there for improvement in terms of integrating aquaculture into the directive as well. And regarding the use of sludge from aquaculture, as I already said, there happen to be some regulations already which make it difficult, at least, to use sludge, animal feces, for example, as feed for other animals. So that is an explicit, that is explicitly forbidden, which is perhaps problematic because when we consider reintegrating the waste into the loop. So that is also there. So I mean, what we could perhaps do is produce a list of recommendations. The iFishIENCi team, the experts here that you could, I was just discussing it with Dominic earlier. We could produce a list of recommendations for the European Union, which perhaps will then be taken into consideration in tailoring the directives so that our research findings, our expertise are of application and use. Yeah. So that's pretty much all from me. Thank you.
Thank you very much.
No problem.
Thank you very much, Eusha, for this information, this complex framework, in terms of regulatory. Thank you very much. Dorothy, I don't know if we have any question from the audience. Yes? Okay, so Eusha, I have a question about regulation. So in terms of waste valorization and circularity, how can be enhanced by the EU through relevant regulations?
Yeah, that's actually a very interesting question. So so as I said, it's very difficult to see aquaculture as an isolated body. So it's a part of nature. And all parts of nature are actually connected to one another. So it's only normal that you would require relevant legislations which make it easier for the exchange, material exchange, for example. So we have been contemplating, just to give you an example, submitting a European Union proposal, which would propose genetically modified trees as a carbon sink, and which would then be used, the biomass produced by these genetically modified trees will then be used to produce biofuel. But we also acknowledge that when you have a genetically modified tree, it tends to deplete the soil faster of the nutrients. And to cope with this, you need to have another source of nutrients, and we were considering whether it's possible to integrate aquaculture into the framework as well, so that we have an extra source of nutrients. So I mean, if legislations exist which help us accomplish such holistic synergies, I think it would be fantastic. Yeah, I think regulations already exist to make this possible, but there is always room for improvement, I think. Yeah.
Yes, definitely, we have room for improvement. Thank you very much.
No problem. Thank you so much.
Thank you. So now it's time for our second speaker. So please, Gianmarco Cusimani from Aqua Biotech Group from Malta.
Hello,
Please.
Malta.
Hello.
Thank you very much for
The floor is yours.
Thank you very much. So, welcome everyone. Thanks, Montse, for introducing me in the second day of the workshop of the iFishIENCi project. Today, I'm going to talk about the general framework for waste management from RAS, performed ABT within the iFishIENCi project, and the Waste2Value product. First of all, I would like to give you a very brief insight about the aquaculture sector. So, as you probably know, the aquaculture sector has constantly grown in the past years, reaching a global production of 87.5 million tons in 2020 and aiming to reach 106 in 2030. So the aquaculture production, to give you an idea, it can be classified based on the degree of intensity and dependence on exogenous supply of inputs like feed in intensive, semi-intensive and extensive. Of course, it depends on the link between the aquaculture production and the environment. So it can be classified in either land-based or water-based aquaculture. Within these two categories, we can find the typical aquaculture production system like float row, RAS and ponds and aquaponics that belongs to the land-based aquaculture, while cage belongs to the water-based aquaculture. Of course, the production of the many groups of farm species differs significantly across regions and countries. Around the world, Norway, Chile and China dominate the world mariculture of finfish with sea cages. In the case of the Nordic aquaculture, Norway is the leading with overall production of salmonids that exceed 99%. Of course, this one is one of the biggest revenue production for the entire region. And however, it puts a lot of pressure on the environment because of the emission that can be distinguished in water emission, so discharged water and nutrients, emission into the air, so gaseous emissions, and emission into the lands, such as mortalities and sludge. Of course, the waste management of the aquaculture sector is mainly important for the land-based aquaculture, and especially for us. So what we would like to highlight today is the role of the sludge in the wastewater, in the waste management. So what is exactly sludge? Sludge is a byproduct of the aquaculture operations that consisting of a mixture of organic and inorganic materials, including an eaten feed, feces, and other organic and inorganic components that settle at the bottom of the aquaculture system, such as in ponds, tanks, or raceways. Of course, its composition depends on the management practice, feed composition, cultured species, and stocking density. As a general view, so we provide feed to the fish that after process of digestion and absorption, they produce a certain amount of waste in the form of urine and feces. Of course, it depends on how well is performed the husbandry in a facility. It can also happen to have an eaten pellet. The chemical characteristic of the sludge that can be distinguished in protein, lipid, carbohydrates, nitrogenous compound, sediment, minerals, and trace elements. As we said before, the waste management is mainly challenging in land-based aquaculture that we can define as a cultivation of aquatic organisms, such as fish, shellfish, and aquatic plants, in enclosed system on lands. Among these one, we can find ponds, raceways, and aquaponics, and today we're going to focus more on the RAS production. I wanted to highlight some pros and cons of the recirculating aquaculture system, but I'm not going into details. What I want to focus more is on the role of the waste management into a RAS production, and specifically as a closed system, we can, of course, produce sludge in different parts of the system and in different form. As I said before, in the form of gas, in the form of foam, solids and liquids. The first approach to the waste management is the separation of solid and liquid, and it can be performed by sedimentation, mechanical filtration, so through swill separator, drum filter and disc filter, but also with thickening using coagulants or flocculants, dewatering and drying in specific facilities. This one is has a cost for a facility, but it can also be, if properly managed, a potential revenue production. In the iFishIENCi project, we developed a product called Waste2Value that had different goals, such as the contribution of the generation of more circular and value chains, the guidelines and recommendation of valorization aquaculture waste stream that it will be described in the next presentation from my colleagues, technical aspect of the waste management, LCA and LCC in the framework of the circularity, characterization of the waste from RAS system, utilization of waste stream media as fertilizer, biogas, biofuel, and platform chemicals, so to give you a revenue of this waste production. And this one was done by a multidisciplinary approach and partnership between Norse, Leitat, EBT, Covartec, and Vitafort. The role of EBT in the Waste2Value development was to provide waste streams coming from a RAS system. In this case, it was a pilot scale system. And we performed 4 different experiments, 2 with rainbow trout, 1 with barramundi, and 1 with hybrid catfish. The methodology to collect and process the sludge was similar in all the experiments, except for the different system used in 2 of the experiments. So basically, what we did was the collection of the sludge through wheel separators, filtration using 100 micron mesh, and final vacuum filtration using 60 micron mesh that is simulate what happens naturally in a drum filter or in a filtration system in a RAS facility. In the case of the trial with the barramundi, the collection of wastewater was done after mechanical filtration, so after the drum filter, and then the following step were the same as the previous experiment. Here in the 4 box, I've highlighted the characteristic of the experiment that we perform at ABT, so the different species that were targeted, just to highlight the flexibility of our system and the possibility to perform trial with different species. Of course, this one was of a great value for the iFishIENCi project and the Waste2Value product, because we could develop and learn from different type of sludge, different condition, and different type of production species into the RAS system. After the collection of the sludge, that it was in the form of raw sludge, concentrated sludge, and filtered water, these samples were sent to our colleague of Leitat and Norse for characterization. And here I would like to just give you a brief highlight on the chemical and physical characteristic of the sludge that we collected. So just to summarize, there were the 4 trials performed with the yellow box and green box in both tables that I've highlighted. I wanted to show you how the concentration of nutrient happened through the filtration. There was an optimization of the storage capacity through the reduction of the volume of the sludge collected, that it was ranging between 5 and 20%, and the production of a valuable byproduct for the industry that you can see here in the green box, where I've highlighted all the nutrients that were retained into the various form of sludge. Of course, this one, in our case, in the case of ABT and a RAS facility, it reflects in a water quality improvement of the system that is of paramount importance for a RAS facility. So, to conclude, the waste stream for RAS have the potential to be reused and valorized under a circular approach and towards zero waste. The outlet water from land-based fish production could be directly used for the cultivation of phototrophic microalgae, such as Microcoropsis gaditana, that was one of the products of the iFishIENCi project. However, the phosphate is mainly limiting nutrient for the microalgae. What we saw during the characterization was that the retention of the phosphate was mainly on the concentrated sludge and not in the filtered water. In the case of the yeast Candida utilis, that was the second product of the project, could not grow in wastewater from RAS due to the low organic carbon content. Of course, as Yusha highlighted before, we need to further investigate the potential bioaccumulation of persistent organic pollutants in yeast and microalgae as feed. Thank you.
Thank you very much, Gianmarco. It's really interesting information about the waste management in the RAS systems, how we have collected all the samples for the experimental trials within the efficiency project. So now is the turn of questions. So if not, I have a question. So Gianmarco, question regarding the presence of salts in the sludge coming from the seawater. So how it could be solved? Is this a challenge that we should have into consideration in the future?
Exactly, so thanks for the question. So yes, it is quite challenging for the aquaculture in general, but specifically for the RAS, because I mean the accumulation of sodium into the sludge, it might be an issue for the growth of the bacteria into the biogas production system. So it can be solved targeting different, let's say, final product. For example, we recently we could use the sludge from the seawater to grow some worms, some polychaetes that then can be used as a feed for fish. So we can grow a biomass that can be reused as a feed, of course, producing a revenue. The sludge can be also used to grow some halophyte plants that can be then used as a feed for livestock, or in general that can be treated as a source of energy, so sent directly to incineration like the freshwater sludge, and then used to produce energy.
Okay, thank you very much,
You're
Gianmarco.
welcome. Thank you.
So I'm the next speaker. I'm going to talk about waste valorization. After these first presentations about the framework in the regulatory, and now the waste management is the turn of the valorization approach. So currently, the waste from aquaculture is allowed to be valorized in different ways. For example, incineration, biogas production, and silage. This is possible, but we can find some limitations. For example, for the biogas production, we need large volumes to be feasible. So we also could consider to apply as direct fertilizer. But again, we can find limitations, for example, pollutants, or that the nutrients are bound to the solids. So in this context, at Leitat, we design a study of research focused on the upcycling of the waste from aquaculture. So the idea was to bring a higher value from this waste. So the objective was to apply different valorization technologies for the production or the development of nutrients, of medium ingredients that we say, and these medium ingredients will be applied for the cultivation of yeast and microalgae. So specifically, we want to recover the nitrogen, carbon, and phosphorus from the sludge and use these nutrients for the cultivation of yeast and microalgae that then could be the feed for the aquaculture. So in this sense, we would like to contribute to the circularity of the aquaculture and to the zero waste approach. So the idea, the objective of the research was to demonstrate the feasibility and the safety of this new way of valorization of the sludge through the scientific knowledge, new scientific knowledge. Well, specifically in this study, we use we design and we develop new technologies for the recovery of the nitrogen, phosphorus, and carbon from concentrated sludge from a RAS system. as the nutrient ingredient for the yeast and algae. So specifically, we used a concentrated sludge with 15–20% of dry matter after the recovered through the 60 micro mesh filtration. And it was a sludge coming from experimental trials with rainbow trout fed with conventional feed. So, well, we organized this study in 3 stages. The first one was the screening of the different methodologies. So, based on literature, we select the most promising technologies for the recovery of these nutrients from a sludge. Then, with this information, we optimize the selected technologies with the aim to maximize the recovery yield of the process. And finally, we reached the pilot scale demonstration in order to validate this technology at a pilot scale and to provide NORS with enough ingredient for their trials. So if we go into more detail, firstly, we designed the process. We start with the pretreatment. So here with the pretreatment process, we need to facilitate the solubilization of these nutrients at the first stage. Then we follow with hydrolysis that can be by chemicals or by enzymes, but the idea is to solubilize these nutrients. Then we continue with the centrifugation and filtration process with the aim to separate liquid and solid fractions. So the idea is to recover the liquid with the nutrients and to remove the solids. And if we continue with the solids, then we apply a second washing with the idea to extract the remaining nutrients of the solids. And after that, we apply a second centrifugation filtration to separate the solid fraction. We can say residue, or we can say coproduct maybe, with a zero waste approach. So it's not waste, it's a coproduct that we can obtain with this process. And after we mix these 2 liquid fractions, and we have the medium ingredient for yeast and algae cultivation. So if we focus our attention on the pretreatment and enzymatic processes, is where we focus our research. And firstly, so we apply different type of pretreatments. We work with mechanical pretreatments, with thermal and chemical pretreatments. And finally, we selected the ultrasound-assisted extraction method as the most promising technology to facilitate the solubilization of these nutrients. And in the case of the hydrolysis, we work with enzymatic hydrolysis, and we work with also chemical hydrolysis. And we select the 2 types of enzymes. We work with cellulases, proteases, and finally we selected 2 types of proteases. And we also select the potassium hydroxide as an extraction technology or hydrolytic technology. So then we continue with the optimization of these technologies. So we use the experimental designs, the design expert program. And here with different type of treatments, we reach the optimization of this methodology and these processes. And we try to maximize the nutrients of the nutrients recovery efficiency, so the nutrients that we can find in these ingredients. And so we finally define 2 different methods. The first one is the enzymatic method, enzymatic technology. So we use the ultrasounds, and then we use the 1.9% of endoproteases and 1.9% of exoproteases with a temperature and during agitation during 5 hours. And we also had a second process a chemical process in this case, using the same conditions with ultrasound-assisted extraction, but also we add, in this case, not enzymes, we use here potassium hydroxide, and at the same temperature and agitation and time. And finally, we repeat the process, the methodology at pilot scale. So both methods, chemical and enzymatic process, was just a scale up at pilot scale using an ultrasound, pilot ultrasound equipment and a pilot bioreactor. So in this case, we achieve the maximum nutrient recovery that we achieve for the enzymatic process was 36% of nitrogen, total nitrogen, and 13% of carbon, and in the case of phosphorus, just 3% of recovery. And about the chemical process, we achieve 46% of recovery of nitrogen, and 60% in the case of carbon, and, well, 8% in the case of the phosphorus. So after the pilot scale, we perform full characterization of the samples. We characterize the ingredient, the medium ingredients with both processes, and we also characterize the residue, this solid fraction. So, well, we don't have time to enter into details, but we perform the physical-chemical characterization and microbiological characterization, and also the metals and contaminants. So, okay, we have medium ingredients, we have solid fractions, and what about the application of these ingredients? As I was saying during my presentation, the objective was to obtain medium ingredients for the production of yeast and algae. And, but we have also other applications in mind. We could apply, according to the characterization results, we could apply this ingredient, these rich-in nutrients, as a fertilizer for plant nutrition. So it could be feasible to apply, according to the results, to apply as fertilizer. And what about the solid fraction, this waste or co-product that I say? According to the characterization, we consider that it could be applied in agriculture. Again, we could be also a fertilizer. And as conclusions, we can say that the treatment of the concentrated sludge from the RAS system, which combines ultrasounds, followed by enzymatic or chemical hydrolysis, proved to be a promising technology to extract nutrients, mainly nitrogen and carbon. And our main recommendations is, of course, we need to scale up a little bit more. We need to reach the semi-industrial or industrial scale. After, we should analyze pollutants. For example, in the case of the cadmium, we should study in the sludge and the extracts that we can achieve this type of characterization. And finally, again, as my colleagues, we should recommend work in the potential bioaccumulation of the POP, the persistent organic pollutants, in the sludge and in the yeast and algae, and as well the ingredients that we produce. So thank you very much. I don't know if we have questions. If not, we will go to the next speaker.
Yeah, there was one question, but you answered it.
Okay.
It was on phosphate removal, so it was about 3% phosphate. That's
yes. In the case of phosphates, we think that we should propose other ways of valorization. So maybe biotechnologies and these type of processes should be the most appropriate to recover the phosphorus. Yes, not with the technologies that we are using in this research. Yes. Yes, so now is the turn of my colleague Dorinde Klingris from Norse. Hello, Dorinde. So the floor is yours. Thank you. Yeah, you can hear me all?
Good. So today I'd like to talk about how we can use the waste that we've been talking about previously by the previous presenters for the production of microalgae and yeast. And maybe just to start very shortly with an introduction about what are algae, because it's often a very unfamiliar word. They're very similar to plants, but where plants differentiate and they have roots and leaves and possibly branches, etc., microalgae or algae are generally clusters of single cells or clusters of cells. And in principle, we can divide them into microalgae, which are the single cells, macroalgae, which are seaweeds. And one of the things that they have familiar is that they can use photosynthesis, similar as plants. So they use sunlight and carbon dioxide to produce their biomass. But at the same time, the word algae is very easy, and we can talk about it as algae. But as you can see here, this is a phylogenetic tree, so it shows how similar different forms of life are on Earth. And as you can see, animals are all considered very similar. They're in one box. It means also that algae are in like all these colored boxes. So it also means that the differences between us humans and a shrimp are like we're more similar than different algae can be. So there's huge difference between the different types of algae. Some of them grow in seawater, some of them grow in freshwater. Some of them make very interesting components like omega-3 fatty acids or pigments. Others are toxic. So there's a huge difference in what they can produce. But one of the things that almost all of them are very good at is taking up nutrients, insoluble nutrients, and even at very low quantities. With the fact that there are some algae that have these very interesting components, that also means that some of these algae can be very interesting as feed ingredient, for example, in aquaculture. So you've heard about this a bit more yesterday, but some of these algae are rich in omega-3 fatty acids and proteins that can be interesting feed components. So in this whole production process of algae, then the question is, can we use waste streams, for example, from aquaculture to produce, again, fish feed in this circular approach? So as we heard before, in the iFishIENCi project, we obtained a lot of different types of waste streams from the aquaculture systems with our partners like Aller Aqua and Aqua Biotech. And that was, for example, fresh water or so-called dirty water, so the outlet water of the RAS systems, for example, producing the barramundi and the trout grown in fresh water. We got seawater and we got the non-concentrated sludge. And as you heard already before, we also got then the sludge that was treated by Leitat. So with the latter, we heard already about it. We got, in some cases, definitely very good algae growth, but it's to be optimized further. So now I'll go into these other waste streams, so the more watery types of waste streams. And what we try to do is we try to test at different scales. Can the algae grow on these waste streams? And if they can, how efficient are they at taking up these waste streams, but also how much microalgae can we produce in the end per liter of waste stream, for example. So we started very small. These are Wells plates. So every little well has a couple of hundred of microliters. And this was a nice way of testing a lot of different waste streams and different treatments, for example, and just to see, can the algae grow or not? We can't get much more information out of it at this level, but it gives a nice starter material. So we tried a freshwater algae, Chlorella vulgaris in this case, which is an algae rich in protein, and we wanted to see, can it grow? On all these different types of waste streams, but also do we need some form of pre-treatment? Because the water directly comes from the fish tanks, so should we treat it, for example, with a heat treatment to see if we have to kill off whatever else was already growing in there in forms of bacteria before we give it to the microalgae? So what you can see here is the growth of the algae. So we see the biomass on the y-axis, and then in time on the x-axis. And what you can see almost on all waters, and this is just a short selection of them, we see that the algae grew very well and very similarly. But in some cases they didn't, and actually many cases they did, but in sometimes when we didn't have this pre-treatment, we saw that there was a culture crash. So pre-treatment might not be necessary, but it might be a nice way of using it to prevent culture crashes from happening. So then we went to the next level. This is what we call small bubble columns. So the algae are growing at 300 milliliters, being illuminated, and they get some aeration to provide them with carbon dioxide. And again, here you can see the time and then the growth on the y-axis. So we had different types of waters again, and then also in some cases we added additional phosphate to see, because based on the analysis we saw already that there's quite some nitrogen in there. But if we look at what we would normally give to microalgae if we have this industrial production process, we would have more phosphate compared to the amount of, or how do you say it, like the ratio of nitrogen and phosphate in the wastewater is more nitrogen and phosphate in such a ratio that it's actually much lower than what we would normally have, so to say. So we added a bit of phosphate to be at the regular levels. And what we saw is that in principle they grew all again very well. If we didn't add any phosphate, we definitely were able to remove 100% of the phosphate from the water. And in cases where there was too little phosphate, then we didn't manage to remove all of the nitrogen. But in principle, they grew very well, and we overdosed probably the phosphate also in some cases. So we didn't necessarily have to add as much as we thought we would. So that was very positive. And then we had a last trial where we tried in these tubular photobioreactors. So these are like the baby version of how we would produce them at large scale. And we got, in this case, we got seawater from a Barramundi trial. And again, what you can see here is the growth. And in orange, that's the control. So that's how we would grow the algae on a commercial fertilizer-based medium. And in blue is the growth on the dirty water from the drum filter from the RAS system. And as you can see, in the beginning, they grew equally fine. But then we see that there's less nutrients in the RAS water compared to what we would have normally in a commercial-based medium. So there, it's just not enough nutrients for them to keep on growing. So based on this, what we saw is that if we would have 1 liter of RAS water, which is this IFN01, we can produce 2.4-ish grams of algae per liter. Whereas if we have our control medium, so then we produce almost double the amount of algae in the end. But still very interesting results. And we, in this case, actually managed to have a capture efficiency. So we consumed 100% of, in this case I say the N, but it was actually both N and, so nitrogen and phosphate that was consumed 100% at the end. So in summary, all these different types of wastewaters coming from RAS systems, they work, and they work very well. Then microalgae weren't the only organism that we tried to test on these waste streams. We also test yeast, which is another form of organism or microorganism. But in this case, they don't need sunlight. They don't grow on carbon dioxide, but they grow on dissolved organic carbon in the water. So also here, lots of different wastes were obtained from the different partners like Aqua Biotech. And that was processed to make then Sutomedia, and here it was tested in these Erlenmeyer flasks, so like 100 milliliter volume shake flasks. And also here you see in time and in the amount of biomass. And as you can see, here it is in hours. In the algae case, it was in days. Yeast does grow quite a bit faster than microalgae. So they managed to grow in certain cases very fast, very well. But here we can potentially say, so again, also this is all the different types of waste, and then in some cases it was just diluted, in other cases it was diluted and then centrifuged and the supernatant was used, for example. And then everywhere it was heat treated to prevent any other things from growing. And what you can see here is that not in all cases there was really significant growth on these waste streams. And very often that probably has to do with the fact that there's just not enough organic carbon in these media to provide them with enough carbon source to build more biomass. But in some cases there is, and then we also definitely see interesting growth. So, concluding, if we look at microalgae and yeast and then the different types of waste, we can see that fresh water directly from the aquaculture tanks works for microalgae, doesn't work for yeast. There's definitely not enough carbon in there. Marine is only relevant for microalgae anyways, because yeast are freshwater organisms. If we look at the non-concentrated sludge, there's potential for microalgae. There is some form of challenge in the sense that particles block the light and microalgae need the light. So that's a bit of how to deal with that type of thing. But there is nutrients that they can use. For yeast, it didn't work because of the lack of carbon. Concentrated sludge doesn't work for microalgae because it's just way too much particles, but works for yeast. And then the pre-treated sludge by Leitat definitely has potential in both cases, but needs to be further optimized. So this is really in summary, waste streams for microalgae, for aquaculture, and for yeast definitely have potential. This was just small-scale trials, so next step would be to go at slightly larger scale, but also to really integrate these processes next to each other, because now waste had to be shipped all over Europe. And what we see is that it's depending on the organism, but for sure the nitrogen components in the waste are very interesting for the microalgae, and the phosphate is very interesting for the microalgae. And in the case of yeast, there needs to be sufficient carbon in there, but then it also forms a very interesting source of nutrients for these organisms. So with that, I would like to thank you for your attention, and if there's any questions, happy to answer them.
So thank you very much, Dorinde. It's a fantastic piece of work. So exciting results, and maybe if you can answer one question, and you maybe started to explain it, but could you bring more details in considering your research and your results already achieved? What will be the next steps? No? What will be the next steps towards the producing microalgae using aquaculture waste?
Yeah. As already also Giovanni before was into, but there's quite a difference in the nutrients in waste, for example, and the levels, which will be based on the fish and everything. So it will probably also fluctuate throughout a period in the year coming from a farm. So one of the next steps would be understanding how this fluctuates, and also to get a better understanding, okay, how much waste comes from one aquaculture plant, and how much of these organisms could you then grow on it, and what would it mean for the size, for example. If you have a plant that produces, I don't know, 10,000 tons of fish. I'm not a fish expert, so don't kill me if that's the wrong amount. But how much algae could you produce, or how much yeast could you produce next to it, and does that make any sense? And I think based on what we've seen, it definitely makes sense, but it might be that you actually become an algae producer with some fish on the side. Is that interesting, or isn't that interesting? So that's definitely up for next steps.
Thank you very much.
Thank you. Thank you.
We will wait for your next research and next results. So now is turn of the circularity assessment. I'm proud to introduce my colleague, Imma Sanchez from Leitat, Spain. So please, Imma, the floor is yours. So,
thank you, Sandra.
You can
oh, yes. Sorry. I'm thinking in Sandra every time when I saw the Waste2Value. So thank you, Monse. Yeah, this is the time for circularity assessment. I promise that I won't repeat again the things we presented yesterday, but I'm afraid that I have two things in common. One is a Mentimeter, and the other one is only one slide. So this is a slide that I presented yesterday. Basically, I would like you to show where is the circularity. Basically, if we have a farm and we are using feed, we hopefully not get much fraction of uneaten feed, but the real thing is we have some particles from the uneaten fraction and also the excretion and the feces. So in the end, we have to find solution to valorize this waste or these nutrients. And the session today is just to cover or to address how much are closer this process to the circular economy. So in this sense, I would like to make you this question about how can we measure the circularity on what kind of performance indicators would you define for a circular process? So yes, we have a minute, I would say. Yeah, exactly. If you have to decide on how much circular is a process, what kind of indicators do you expect to measure or to evaluate? It's a difficult one, eh? Basically, it's the question that we have been asking ourselves during 5 years, so it's not an easy. Okay. Okay. Reuse potential, diverse products, waste amount, waste, okay. Recovery efficient. Okay. Thank you. Let's see if we are aligned with the feedback received. Well, during the execution of the project, we identified several tools to measure circularity. There are some open. You can check it online, and you can model your process, obtaining some key performance indicators. But the thing is, any of these tools have been developed for aquaculture systems, even for biological cycles. So in the end, we cannot use it if we want to go more in detail in the efficiency of the circularity system in aquaculture. So that's why we started to think what we should measure, if we had to measure the process, if we had to measure the product, or if we look into the whole system or the aquaculture in combination with other sectors as a global scale. So we started to think that if we could measure the circularity of the feed, we could measure the circularity of the farm, we'd also measure the circularity of the waste valorization route. So in the end, we are measuring the circularity focused on the product, on each of the individual products that we can obtain from these individual boxes. On the other hand, the aquaculture has the potential to provide new resources for other industry, let's say cosmetics, for instance. So if we provide resources for others, again, we are being circular, let's say. So in this sense, there are some resources that have been used by others, then the other have some circular attributes, but also our system is circular. This is more focused on the process. And we started to think on the product approach, and we started to evaluate the different waste streams. And we saw that if you don't have an evaluation on the feed production, we won't see the complete picture. So you have to integrate the feed provider, the farmers, and also the waste management part. So all the things together give us the picture of the circularity performance. So in this sense, we identify key parameters oriented to the evaluation of the virgin components in the feed. That means virgin is that doesn't came from a circular or a valorization route, the efficiency of the recycling process, the generation of waste that is not recovered, the fraction collected for valorization. So some of the key parameters have in common some things with your feedback collected before. So the portion of raw materials input flow, it means we will look into the recipe of the feed, also the restorative materials that you are using. If you are using soya in your recipe, these materials should be extractive under a restorative perspective. And the utility of the product, we started to evaluate how well the feed are performed in terms of digestibility. Because if you have an incredible recipe using many different sources, circular sources, but in the end the fish is not happy, they are not integrating all the nutrients for growing, then you won't have a higher circularity in their system. You have to integrate everything together. And these key parameters were converted into key indicators. One of the key indicators, we are not inventing anything. I mean, this indicator came from Helen MacArthur Foundation, but it was designed for technical cycle at the beginning. Basically, we see that if the feed is, should be, the circularity indicator of the feed should be defined in accordance with the recipe, with the amount of nutrients that came from circular routes. But also another factor that should be interpreted like the nitrogen assimilation efficiency of the feed. So if we compare how much ingredients you get from this linear process or circular process and how much is the performance, how well is performing the digestibility of this recipe, in the end we have the material circularity indicators. Therefore, we could expect that the higher nitrogen assimilation, the higher utility, then the higher circularity. We put everything together and we try to make a benchmark between us, between the different trials in the project. So if we are working together with the different indicators in terms of the feed, also the material circular indicator, the nitrogen waste, and also the zero waste index. The zero waste index is telling us the potential of recovering nutrients and other ingredients for other industries, not only for being used in the aquaculture. So we have different targets. If we are looking into the linear flow index, we want to have 0 values. On the other hand, material circular indicators should be close to 1. And then you have the target indicated in green column. In this sense, we could make this kind of benchmark, this kind of exercise to evaluate how the different waste streams collected from the trials in the project could be more or less interested in relation to the circularity attributes. So if the microalgae or if the yeast could grow with waste streams from aquaculture, with the nutrients flows from aquaculture, we could say that the industry have 0 waste attributes in the sense that they can have the potentiality to find other value chains. So in the end, we have a comprehensive picture on how the iFishIENCi project performs in the circularity. So that's all from my side.
So thank you very much, Gemma. I have a question. Maybe it's a challenging question, but well, we have a challenging topic. So please, is there only one magic solution to achieve the total circularity of the aquaculture system?
Well, actually, no. There's no only one answer. You have to be more, I think from my perspective, we should work together with others to find the solution, but again, it's not only one solution. I mean, if you are looking only into the feeding system, you are very oriented to the production, let's say, or to the fish behavior or something like this, but also you have to integrate the other perspective from the potentialities of the waste. So I think that you have to see all together, and in the end it's a balance between the recipe of the feed, between the nitrogen assimilation, between also the waste recovery potential and the efficiency of the recovery of these nutrients in the waste stream. So if you don't see the complete picture, it's not possible to see how are your circular.
Thank you. Perfect. Thank you very much, Imma. You're welcome. So now, last but not least, our last presentation, we have Kate Bocadoro online from North. Kate, yes. Hello, good morning.
The floor is yours.
Good morning.
Good morning.
Good morning. Sorry I couldn't be there in person today, but I'm glad I could at least join online. Okay, you should see my screen.
Not for a moment, one moment.
Okay, so today I'm going to talk to you a little bit about the work we did within iFishIENCi for looking at other valorization routes for the waste, and looking into starting to discuss how this can lead to new guidelines and tools to improve the current system. So just a quick context on this, of course, when we're looking into waste and biomaterials, what's important at the moment is we are shifting from oil-based industry to more sustainable resources and bio-based products. And in this context, it's important to look into limiting the use of resources and also limiting waste and making the best use of waste. In this context, the use of industrial biotechnology has been extremely useful. This is a process by which we can use microorganisms to transform waste compounds into feedstocks. And the idea here is to basically not have waste anymore and basically be able to treat waste as a valuable resource and optimize what it can be used for. So quickly on industrial processes and the use of microbes. They have been used, microorganisms such as yeast, bacteria, fungi have been used to produce a wide range of compounds. They can be used to replace all sorts of compounds which are currently petroleum-based for new bioresources, also enzymes and biomaterials. And this tree long way using sugars and starch and feedstocks which are not very good in terms of use of resources, but also they can get expensive. But the ability of microbes to be both transformed and actually their natural abilities mean that they are able to actually degrade a really wide range of compounds and then be engineered or naturally produce a wide range of compounds which are useful for us. And so the types of waste that have been used have been waste from agriculture, aquaculture, feed industry, food industry. Microbes can also use gases such as CO2. and the type of compounds that can be produced are very, very wide and almost unlimited due to genetic engineering. But we currently can produce biomass, proteins, fatty acids, enzymes, antibiotics, and one of the limitations of this industry, and why it hasn't picked up more than it has, is largely due to production costs. And one of the ways of reducing production cost, of course, is to shift towards using waste compounds and compounds that are currently very low value to produce higher value compounds. And the idea, of course, when we're looking at waste is to produce as much of high value compounds as possible. So looking into the waste and looking at what it contains and how it could be used better to extract high value compounds is extremely important. So you've seen this picture earlier today, and the route you have seen that Dorinde, my colleague from North, has talked about is looking into the waste to produce the feed, which was used in iFishIENCi, the candida and the algae. But actually, this is of course a very neat circularity, direct circularity. This production and using the waste could also be used to produce many more compounds. It doesn't have to be necessarily feed. It can go into other values, other pharmaceutical compounds. And if you look at the pyramid of value chain, what we basically want when we have the waste is to first foremost produce high value compounds and then use as much of the waste as possible. So in the test we did here, we couldn't test a huge number of different waste, but we looked into particularly two, which were quite actually similar RAS productions with small differences. And the reason is we also wanted to look into how similar they are, how similar waste produced are, and what kind of differences do we see in terms of what they can be used for. And if we look into these two that were tested, is the size of the fish that the sludge was extracted from, and the feed was also slightly different with more protein and minerals for the adult fish. And then we also actually tested the enzymatically digested sludge in case actually that most of the nutrients were not accessible. So if we look into this is the sludge composition itself, and I won't go into detail here, but just to show you that actually the two sludge compositions were quite similar. Main differences being small pH differences, small mineral differences, quite a big difference in the organic nitrogen. And then, of course, in terms of what sources of carbon and exactly what sources of protein are in there, we don't know, and we don't know how accessible it is. So maybe before you look too much into this, so what we did when we took the composition is what we first looked into is basically having a quick screen of classic industrial production organisms to see if they could actually use the entire sludge as a source of feedstock, and feedstock meaning source of carbon, energy, nutrients, without adding anything else. And this was a little bit of a shot in the dark because organisms typically need a very defined, precise media, often with vitamins, with trace minerals, and a fine balance of the right carbon source. So but we wanted to do this because it's a great way of limiting what needs to be added and limiting the cost of the industrial production. So we looked into different industrial processes, and we chose looking into biomass production, lipid production, enzyme production, and general organisms that produce chemical compounds. And this was to have a look into feed food industry, pharmaceuticals, and different compounds, just to look at the general potential. And these here on the right are just the listed organisms that we looked into. And so very quickly, these are the organisms on the left that we investigated. This is the first sludge sample we got. Search for it should make all the nutrients more available. Standard media, I just wrote this down because it is the media that the organism would normally need, which is quite a complex media. But if you look generally into this, so the first thing we can see is actually a lot of these organisms grew very well. And again, this was on the sludge on its own. It had no addition of any kind. So actually, it grew also on the enzymatically treated, but actually in the case of these sludges, it was not necessary to treat it because the nutrients as they were already available and good to support growth on many of these organisms. So looking to very well on sludge alone, and showing that actually it could be a very good source of a feedstock to produce biomass, lipids, and a wide range of chemicals. And that's very, very good news, and definitely needs further exploration. So looking at further exploration, basically what it looks like is that what we need to do is analyze different sludges and screen potential routes, because there are clearly variations between sludges, and very subtle variations can be due to small components missing to support growth. So ideally, when looking into processes, we would want to optimize the growth, maybe supplement with some minimum compounds to get very good yield of the product we want. And this actually involves mainly putting industries together and building a really good network of industries and really good collaboration, so that the waste of one can become basically the resource of the other. And this could include, of course, the aquaculture industry, but biofuel producers, enzyme producers, animal feed producers, also food supplement industries for high quality proteins and lipids. And basically getting together and putting up projects and policies and guidelines to basically make the most out of the waste. So here I want to open the floor a little bit, because when we were looking into guidelines, something we definitely see is needed is some kind of support system to be able to evaluate the waste, the potential value of the waste, and the potential valorization routes. And for that, a lot of data would be needed to be able to compile data sets on what all the different wastes are, what the components are, which components can be used by the microorganisms, and then also look into what organisms are the best for producing for different industries. So it takes what we had thought of was something like a website or something a little more interactive than leaflets. Of course, leaflets can be done, but this is much less dynamic and doesn't allow for input. So I'll open the floor here in terms of what you as industries and researchers see as the best kind of support system to build guidelines. I don't see the questions on my screen or suggestions from people here.
Yes, do you have online questions?
Yeah, Kate, hello, thank you for your presentation. There is a question that I had, just a quick clarification, because I noticed it seemed to me that the sludge was similar for the two RAS trials, even though the sizes of the fish were different.
how important, or is it relevant what size the fish are in the RAS system as far as the composition of the sludge? Because I noticed that yeah.
So I suspect it is only important in the sense that the diet is quite different, and the diet has quite a strong influence on the sludge composition. And the reason is, of course, the sludge composition also includes particles from the diet, which are then found in the sludge. So, yeah, the diet makes a difference, and the conditions for growth for the fish, I guess, are also different. In terms of size, actually, something that's quite important in this context is the size of the aquaculture and the amount of sludge, because a lot of these production industries actually will require a lot of feedstock. So something that should be looked into is pooling of sludges from aquacultures in different places, which could mean that it becomes also a little bit more even in terms of composition.
Yeah, I'm Krista from Ovum, containment systems. Thank you. Yeah, and it's of course very interesting. And I don't work with RAS systems, but it's floating in the ocean, so it's a little bit different technologies we're looking at. But a lot of what you're sharing is very interesting. And my question are several questions. As you mentioned, there's these opportunities to make like online web-based some information connection platforms, but like for the technologies to be implemented in industry, where does this roadblocks or like the next steps lie? Is it the industry just not knowing about their opportunities, or is it more research needed for the technologies to be like realistic to be implemented?
I think it's both, and it's also a game of putting industries together, because what a enzyme producer might not know is that there actually is a source of feedstock that is of interest, and the aquaculture industry in turn might not know who to turn to. So I think there is a need for an intermediate to plug in people with each other and look into this. So it could be that on a project that would be needed is something looking into many different wastes, analyzing them to look at the variation between them. And this could be something where industry could actually directly put that input into a web interface. And as people start doing that, there would start being some statistics actually on the composition and on what the best routes for optimization are. For the industries that are producing, for them to know the amount that is available and how much variability there is important, because yes, there will be need for research to look into different feedstocks, but it makes it a lot easier if we know what variation there is and quantity there is and reliability and also the origin of it and how it needs to be treated.
Yeah, and I would mention also the technology availability and maturity for the industry to go into the projects and to implement. That's an important part of the picture. It has to be economically viable. And I like you mentioned some notes on it, because of course a lot of the research is very early, so it's a bit too early to look at whether this actually could be an economically feasible.
The low-hanging fruits are the industries that are already producing through biological processes, like some enzyme producers, and those are low-hanging fruits because they already have the technology. It's just a case of replacing the feedstock with something more sustainable. And then, of course, there are a lot of new value chains to be built.
Okay, so this workshop is finished. Thank you very much, Kate, for your presentation. And so
really interesting result, really interesting research, but a lot of work is still pending. So, well, we need to work and to put a lot of efforts in aquaculture and circularity. So now it's time for the coffee break. It's just 5 minutes of coffee break. So we will start the round table, the next session at 11:40 in 5 minutes. Okay, we can say in 5 minutes. Okay, thank you.